Hi, my name is Nicholas Varghese, and today I'll be presenting my Physics 2 Lab 3 covering bar magnets and the interactions they experience. The primary goal of Lab 3 was to observe and measure the magnetic field of our bar magnet. In this lab, we specifically looked at the distance dependence of a bar magnet, its magnetic field, and how the numbers differed from our observed values and our calculated values. For our calculated values, we will be using the equations for on and off axis magnetic fields that we derived from Biot-Savart laws. At the completion of this lab, we will hopefully gain a better understanding of the relationship distance and position have on a magnetic field and its magnitude. In order to fully comprehend and complete this lab, we will need to have a basic understanding of some physics formulas and principles, the first of which is Biot-Savart law. As we previously mentioned, this law and equation will be useful in deriving and calculating the magnetic field of our bar magnet. As you can see in the next bullet point, this is the derived formula, which directly relates the separation distance of a magnet and observation point with the magnitude of the magnetic field. It will also be important to have a basic understanding of Earth's magnetic field and how this could possibly impact our observations and recordings. To begin this experiment, I downloaded a magnetometer app to track the net magnetic field and the magnetic field direction in both the Y, X, and Z direction. I then placed my phone so there was no other magnetic interference other than the Earth's magnetic field, and so that my phone was also aligned with Earth's magnetic north and south axes. Then I calculated the distance dependence at different distances from the bar magnet in order to determine a value for n. Here you can see the observations and data I got from my experiment. On the right, you will see the data recordings from the magnetic field at different distance displacements as well as the results across multiple attempts. The yellow highlighted cells indicate the individual attempts, while the blue boxes are the corresponding averages for each of the various displacements that I measured the magnetic field at. We calculated n parallel by graphing the natural log of the distance versus the log of the magnetic field found on axis, and then took the slope of this linearized equation, which was 3.070. Using the same process, we were able to calculate n perpendicular and therefore calculated the net magnetic field to be 3.34 times 10 to the negative 5. After finding the distance dependence, I was able to calculate the magnitude of the magnetic moment of the magnet, mu, using the value of the intercept, which represented ln of k. Therefore, using Biot-Savart laws, I was able to get the distance dependence formula. I was able to get mu, which was 1.482 amp meters squared. There were two main observations I made during the completion of my experiment process. The first was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. In comparison, the second observation I made was that as the magnetometer was moved closer to the magnet, the measured x component of the magnetic field increased. The following is my GlowScript code to create the computational model of the magnetic field. To do this, I began by creating a function for the magnetic field for a dipole at a specific location, and then used 2 axis and 4 perpendicular locations, which were used as observation locations to create the arrows. Each of the locations then had a magnetic field, and the calculations for that can be seen above. Then the rest of the code just finds the average magnitude of the field at an observation location 45 degrees from another observation location. I then used dperp to create the arrow representing the field at the observation location. To the right, you can see the final output of my model. The white arrow in the center represents the magnet. The 2 orange arrows represent the magnetic field on 2 axis locations. The purple arrow shows the magnetic field at a location 45 degrees from an axis, while the blue arrow represents magnetic field perpendicular to the axis. In this model, we found B net to be 3.34551 times 10 to the negative 5 for our experimental field, while the computational model found it to be 3.58 times 10 to the negative 5. Lastly, we will answer some concluding questions. So what if I had laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? If I had done this, my results would have changed because the magnetic field of Earth would have interfered with my data. I would not know which part of my data would be due to the Earth and which would be due to my bar magnet, and therefore this would skew my results. In addition, if I were to redo the experiment and use 2 identical magnets stuck together end to end, my measurements would differ because the magnetic field would be greater and the distance dependence would be smaller. This concludes my Lab 3.